Welcome, everybody. My name is Yun Gong. I'm a professor in food safety and global health in the School of Food Science and Nutrition in Leeds. My interest is focused on assessing the impact of foodborne mycotoxins and other foodborne chemical contaminants, how they impact on human health, and also developing effective intervention strategy to protect public health from these chemical contaminants. So it is this interest that joined Laura and me together that I'm going to introduce this speaker today. First, it is my pleasure to welcome you to this video seminar of the Global Food and Environment Institute, also GFEI. The title for today is Emerging Contaminants Pollution Across UK Agriculture Soils, which will be presented by Professor Laura Carter. Laura is a professor of food environment chemistry at the University of Leeds. Laura's research focuses on understanding the fate and uptake of emerging chemical contaminants in the natural environment, with a particular focus on soil plant systems. As I know Laura from a little bit of history, Laura joined the University of Leeds in 2018 as the University Academic Fellow. In 2022, she became a associate professor and a research group leader. She holds a very prestigious UKR Future Leader Fellowship, which funds her project entitled Contaminants of Emerging Concern in Agriculture System, a Risk to Soil and Plant Health. So this project was to establish a science platform that uses multidisciplinary approach to evaluate the global risk of chemical in agriculture system. Through a combination of laboratory and field work, Laura's work will offer a fundamental change in how we assess the risk of emerging contaminants in the environment by combining expertise in the field of agriculture, soil, and plant health. Yes, it is this joint interest that in the chemical contaminants food safety risk assessment that connect Laura to me, and we have the pleasure to work with Laura in developing the MASIC online open course we call the MOOC, on food safety and nutrition, a global public health perspective, which was very successful. So just a little bit of information about GFEI. GFEI is the Global Food and Environment Institute, is an interdisciplinary research community. It brings together members from across academy, industry, and public policy to work together on integrated challenges of food security and climate change. And for further information, you can visit the GFEI website, which is posted in the link in the chat. And this seminar also is a part of a series of the GFEI seminars. So please check the check function in the link to our series advised on also Eventbrite and other websites. You can also look at it from YouTube for the recording. Before I welcome Laura, I'd like also to remind you the seminar etiquette. Please ensure your cameras and microphones are switched off for the duration of the seminar. The presentation will be about 20 minutes, during which time, please use the chat function to post your questions. Afterwards, I will collect the questions and will ask the questions to Laura. So there will be about 10 minutes Q&A session. Okay, so I also want to remind you this seminar is recorded. And please be aware of this, and the recording will be available later from YouTube. So now I welcome Professor Laura Carter. Laura, is yours.
Thank you very much, Yun, for the introduction, and to the Global Food and Environment Institute for the opportunity to come and talk here today about some of the work which we're doing in the School of Geography. I was actually looking back because I did a GFE seminar a couple of years back, and this was a really nice opportunity to introduce the start of some of this work. And now I'm really excited that I can come back and actually share with you some of the results from the experiments and the monitoring that we've been doing. So I just want to also highlight that this work that I'm going to present is very much driven by my wonderful research group. So John, Andrea, and Felicity were really the people that were pushing this work forwards. They were going into fields, collecting samples, doing all of the analysis. So I wouldn't be here and presenting these results without them. So it's yes, an opportunity to acknowledge the wider efforts that have come to make this work happen, really. So to start with, I just want to introduce the topic of environmental pollution. So this picture on the right-hand side of the slide is really what I think when you talk about environmental pollution, what you'd typically expect. So you've got atmospheric pollution, you've got plastic litter in rivers, and these, I think they're quite, they're forms of pollution that we're aware of because they're visible. You can see them in the environment. Our interest in the group is around emerging contaminant pollution, and quite often many of these contaminants are not visible to the naked eye. So unless you know they're there, they go relatively unnoticed. And for those of you who are not so familiar with this concept, so emerging contaminants can really be defined as substances that are not traditionally considered pollutants, but they have recently gained attention due to their potential or actual demonstrated harmful effects on human health or the environment. So many of these contaminants are used in everyday lives and are considered beneficial contaminants, beneficial chemicals, sorry. So this could include things such as toothpaste and sunscreens. But then they become emerging contaminants when they're inadvertently released into the environment. Now, in the UK, there's been a number of studies which have shown that emerging contaminants are present in UK waterways. So you may be familiar with this work because it's the press has picked up on this a number of times. And this is linked to mostly sewage discharge, which has been demonstrated to result in the release of emerging contaminants, such as pharmaceuticals. So frequently detected pharmaceuticals or medicines include analgesics for pain medication, beta blockers, antidepressants. But what we're interested in is the concept of emerging contaminants in soil and agricultural systems, because this is an aspect of the environment that is quite often overlooked. So we are interested in emerging contaminants in soils, and the main pathways by which these contaminants can enter soils is following the use of animal manures and slurries and treated sludge from the wastewater treatment processes when these products are recycled onto agricultural land. So they're used as agricultural fertilizers because of their high nutrient organic contents. And the high costs associated with these disposal means that it's seen as a beneficial practice to create a resource that can be land applied and can meet the crop demands and prevent this costly incineration. Now in the UK, we use manures and we apply biosolids to soils, and the typical biosolid application rate is, I think it's capped about 250 kilograms of total nitrogen per hectare. And recent estimates have suggested that between 3 to 4 million tons of biosolids are applied annually. And this is equivalent to about 75%, so 3/4 of sewage sludge production in the UK. Now, for manure, it's been estimated that nearly 100 million tons of manure are applied to agricultural land each year. And depending on the type of manure, so whether this is cattle slurry or poultry manure, application rates can vary, but they typically are between 20 tons per hectare to 50 cubic meters per hectare, and that's for pig slurry. So as you can see, these resources are widely used in the UK, and they present a pathway by which emerging contaminants can enter the agricultural environment. So we identified that there was no UK level farm data for emerging contaminant presence in soils. So soil monitoring studies in the past have largely focused on what we would consider traditional pollutants, so things such as heavy metals. And globally, there's been an interest in research which has shown that biosolids and manure can introduce these emerging contaminants into soil. So we wanted to understand what contaminants were present in UK soils following the reuse of these resources. And this came, the idea of the SPADE project, this is where this came from. So it was really to understand the chemical pollution profile of soils in the UK. So we devised a sampling campaign and collected soils from farms with a recent history of organic soil amendments. So this predominantly focused on farms that had received biosolids or treated sludges or manure. And the first part of the process involved trying to establish some of the previous history of the site. So the timing of application, the frequency of application, and the type of amendments that were used. And then we either went to visit sites directly to take samples, or samples of soil were sent to us in the post. So we focused on the top 10 centimeters after vegetation was removed. And the farms which we were able to get involved in the SPADE campaign included farms that had a diversity of different uses. So there's arable farms, mixed livestock, there's organic farms as well. There was a wide variety of sort of different exposure settings that we would be considering. And in total, we had 400 samples that came to the university to analyze. So this is just highlighting where some of the sites were that we had samples shipped to us, as well as the ones where we went to visit the farms directly. So when the soil arrived at the University of Leeds, we've taken a chemical analysis approach that involved two types of analysis. So the first type was non-target screening, and this was really designed to create a chemical fingerprint of the soil sample. So quite simply, what it's enabled us to do is determine whether there's the presence or an absence of a chemical. So we cannot determine concentration from this data, but it takes this sort of broad screening approach to understand what is present. Now, as you can imagine, this involves huge amounts of data processing, and this is consumed a lot of time to get to the point where we're able to get some usable data. But I think the value in this is really showing the chemical complexity that exists. And then we complemented this with targeted analysis. And this was where methods were developed in-house for a predefined list of chemicals that we expected, or we hypothesized would be present in the soils. And these targeted methods enable us to determine the presence and the concentration in the sample. So combined, we've got these two approaches to give us a picture of the soil pollution in the soil samples. So just briefly, the sampling actually in the fields where we went to collect the soils from involved using a W sampling approach. So where we took 5 samples of soil across a field to really try and get an understanding of the distribution of the chemicals in the soil. Sample preparation steps involved sieving and preparing the soils in the laboratory to ensure a homogeneous sort of sample. There was then a sample extraction procedure that was developed that involved different stages to try and draw out as many chemicals as possible. And because of the trace levels that we were working at, the samples were concentrated using solid phase extraction. And then we used the 2 analysis techniques that I introduced. So we've got the non-target screening and the target quantification analysis. So before I present the results, just to to, I guess, provide a bit of insight into the chemicals that we had targeted in our sort of prioritized method. And as you can see from the selection of chemicals on this slide, there was a range of different chemicals. So we've included chemicals that you would typically associate with being present in agricultural systems. So we've got herbicides, for example. We've got quite a lot of veterinary antibiotics. But then we've included some chemicals that are for human use or human consumption. So we've got personal care products and medicines that are prescribed to treat various diseases or to offer some alleviation of pain, for example. So this is really quite a diverse set of chemicals, very different physicochemical properties. But what we were really trying to identify were chemicals that we thought would be present in the soils and perhaps had been previously identified in monitoring campaigns elsewhere. And these are the chemicals that we focused on. So in terms of the results, what I am able to share is that we were able to detect or quantify a range of different chemicals from this targeted list in microgram per kilogram concentrations. We were able to identify some chemicals, but they were below quantification limits, so have not been reported. The high resolution mass spectrometry analysis I'll go into in more details. So this is the non-target screening approach, but this really enabled us to expand the chemical entities that we were interested in. And some key sort of take-home messages before I get into the actual results, I guess, were the fact that the chemical presence was not homogeneously distributed within a field. So when we took samples from a W sampling strategy, we could see detections in, for example, 3 or 4 of the samples, but not always consistently in all 5 of the samples. And I should say, we also took 3 sort of sub-replicates at each of the 5 points. So we don't think this is an artifact of the analysis. We think it's representative of the fact that you've got a sort of a range, a diversity of contaminants in the field, but this isn't equally sort of distributed across the field. We found that previous application history to the sites was really important because some chemicals were identified as being present in the soils when the previous year's history would suggest that isn't the case. So just to provide an example of this, in a manure amended field, we could see some levels of human use chemicals, which wouldn't make sense at a sort of a first pass of the data. But then when we dug into the site history, previous years had biosolid amendment in the field. And so what this is showing is that there's the presence of these human use pharmaceuticals, that's human use chemicals, that's really persistent, and it's sort of, yeah, it remains present in the soils even following the use of additional soil amendments on top of the biosolids. Another interesting result that we were able to find was that when we started this analysis, we were trying to have a control or a reference site. And what we set out to do was collect samples from hedgerows. So these would be soil samples that have a similar composition to that of the site where the biosolids were added to the field. But they, in theory, hadn't been in receipt of the organic amendment directly. But the results that we were able to see quite early on is that the hedgerow samples were not always controls. So that we saw detectable levels and a range of different chemicals present in the hedgerow samples. So we think this is potentially due to a number of factors. So there could be leaching from the main field into the hedgerow. But what we were also able to establish through talking to farmers was that sometimes when there's an additional material, either the biosolid or the slurry or manure, then this gets put onto the hedgerows rather than being spread on the field. So it does go to show sort of how widespread the contamination is in the fields. So moving straight on with the analysis and the results for the targeted work that we did. So here's just a snapshot of 4 of the chemicals that we were able to identify. So enrofloxacin and ivermectin are veterinary medicines, and we were able to see them in 4 of the farms. I should say here that all of the farms are anonymized. So everything is presented just as a farm number. But we have that site history that we can integrate to try and explain and to look at the data in more detail, but we're just not presenting the data from the farms as identifiable areas. So yes, what we were able to see was that veterinary medicines are able to persist in soils following manure application. So ivermectin was detected up to concentrations of about 36 microgram per kilogram. We also have the presence of human use medication. So here we've got metformin, which is an anti-diabetic, and lamotrigine as well. So this is used to control seizures in people with epilepsy. And this was also detected in soils that had been in receipt of these organic amendments. So here's some of the other analytes of interest that we were able to detect and to quantify in the soils. So we can see the presence of carbamazepine and clotrimazole in 4 and 9 farms respectively. So these again are human use medications. So something that you'd not typically associate with being present in an agricultural setting. And carbamazepine and clotrimazole, we know, are fairly persistent during wastewater treatment, so they're not removed. So their presence in the soil was to some extent expected based on other monitoring campaigns, which have also seen this elsewhere in different countries. But what was interesting is some of these detections were following the application of biosolids 2 to 3 years previously. So it really does go to show the sort of persistence of some of these chemicals. So diazinon, an insecticide, I think it's one of the most widely used active substances in sheep dips. So this was detected in a large number of the farms, and I think this is to be expected. The concentrations were up to about 50 microgram per kilogram. So lastly, the chemicals which I wanted to highlight from the targeted analysis were oxytetracycline, sulfamethoxazole, and tylosin. So oxytetracycline was pretty widespread presence in the farms, and we were seeing concentrations up to just over 100 microgram per kilogram. Tylosin, again, is another veterinary medicine, and these are all widely used in agricultural practice, but it's showing that they're not degraded and they're not as easy to sort of remove from these systems, because following their application to soils, they are becoming persistent in the environment. So now I'm going to just move on to provide an overview of the non-target analysis. So just to confirm, again, this was the idea of trying to determine presence in the soils without defining a concentration, but just looking for presence and absence. And this meant that we weren't necessarily limited to a particular class of chemicals. It enabled us to take that broader view. And this results were able to show that we were able to see over 200 different chemical entities that were detected in the soils that we had as part of this campaign. So interestingly, we were able to see insecticides, fungicides, herbicides. So again, you would expect these for use in agriculture. We could see the presence of natural products, so mycotoxins, flavonoids, plant metabolites were also detected using this analysis technique. But again, probably not so surprising, as I've just presented the results from the targeted analysis, but what we were able to see is the presence of other chemical classes not expected to be present in agricultural soils because they're not used routinely in this setting. So what we were able to identify was a range of different pharmaceuticals, plasticizers, and research chemicals, and these were the chemical classes that were reported to the greatest extent. Phthalate esters were routinely detected, so these are used as plasticizers in coating products in adhesives and sealants. The pharmaceuticals that we were able to detect were both of human and veterinary use. And we could also see chemicals used in research and dyes that were used in textile and paper industries. So just to provide a bit of I guess, a broader snapshot of the results that we were able to see in the soil. This is a heat map from some of the farms which we are working through in terms of data processing. So just to highlight, so this is 22 farms have been included in this analysis, and these are the chemical classes which we've identified to date, but this is some part of ongoing work. So we need to work to refine this and to keep going to look at different libraries to see whether we can improve the chemical identifications that we've got already. So just to highlight some classes, as I pointed out on the previous slides, so we could see levels of plasticizers and pharmaceuticals, surfactants as well across multiple different farm sites, and personal care products as well. And these are typically associated with biosolid amendments. So just to highlight pharmaceuticals in a little bit more detail. So the top pharmaceuticals that were identified as being present included antibiotics. So again, from human and veterinary use. We could also see steroids and a range of different sedatives as well. So I just want to finish my slides by, I guess, trying to come to some conclusions in terms of what does this mean? Because when I've presented this data before, and when there's always the concept of the presence of contaminants in soils, there's always the questions as what does this mean for me? What does this mean for agriculture? And I think at the moment, the results have shown that there is the presence of these chemicals, so much more work is needed to actually try and understand the consequences of this. But just to highlight what we do know, so some work that we've done in our group, but elsewhere as well, has demonstrated the potential capacity for these chemicals to be taken up and to accumulate in crops. Antibiotics in particular have been observed to alter microbial community composition. Some of the work which we're doing at the moment as well is looking at the toxicity of these chemicals to crops and their potential to influence plant growth and development. And as with respect to implications for human health, this is something which is largely unknown at the moment, but much more work is clearly needed to try and ascertain the risk. So yes, just my final slide, I wanted to highlight some of the ongoing work that we have in our group, just to link in where this project sort of sits. And yeah, so we're trying to really answer the so what question. So we've been able to identify their presence and what does this now mean? So we've got a number of different projects which I'm happy to explore or follow up later if you're interested in learning about the work that we've got underway at Leeds. So yes, thank you very much for the opportunity to talk and come and present some of the results from this campaign. And again, I just wanted to highlight that this is a massive collaborative effort that's really been driven by these postdocs. So thank you to John, Felicity and Andrea. And yes, that's it. I'll finish there.
Thank you, Laura. Thank you, Laura, for this very exciting report. I think the study is also very novel in terms of getting useful information, largely unknown information. Now you are starting to discover this. Let's go to the questions to see what's there first. I think Guy has a question. What do you expect to see if this was repeated for deeper horizon below 10 cm?
That's a really good question. So we that was actually one of the first questions we had when we started to get these initial results back in the preliminary data. So what we've done is focus in on a couple of the farms in this spade campaign, and we've gone back, and what we've done is a temporal study where we've collected samples over the course of a year that have taken soil cores, which go down to 30 centimeters depth. So perhaps I can come back in a couple of years or some time in the future and actually talk to you about specifics of what we've been able to find with reference to these farms. But I guess based on research in the literature, there's the potential for the chemicals to leach through the soil profile. So we know that they can enter into groundwaters. So these chemicals are very mobile. And what we've been able to show is that they're persistent, and this persistence combined with the mobility means that there's the opportunity for transport. So they can move on the soil profile. It depends on the chemical of interest. If you've got a really sort of mobile hydrophilic chemical, I think you'll be able to see the movement through the soil profile to quite some depth. We know antibiotics can migrate, and we know they can move down. They've been detected at 30 centimeters, but there needs to be, yes, more work to look at a wider range of chemicals to understand their behavior across a range of different soil profiles.
Thank you. Ellie asked, was there any difference in results by farm type? And is there any organic farms has any difference in terms of the finding?
Yes, so there was differences between farm types. This is something that we're trying to work out at the moment. But I think, as I alluded to in my talk, it's quite difficult because some farms have had different uses over the years, or different applications of different amendments. So it's really hard to try and unpick and create clear linkages between a particular farm use and an amendment type. But what we've seen in farms that are dairy farms predominantly, we can see antibiotics in soils when the waste from the dairy is then used on the agricultural land. Where there's arable fields, it depends on the amendment type, because some of these are manure amended fields, some are biosolid amended fields. So there are definitely differences between farms, but it's hard to make clear linkages as to what the source of the contamination is if there's been multiple applications and the types of chemicals that are present.
Thank you. Thank you. Isabel asked, which type of pharmaceuticals did you find most alarming to detect at any detection level? Were there any pharmaceutical that were detected that you didn't expect to find?
I'll answer that question in a different, I guess, because we were targeting them, we had an inclination, or there was a theory as to why they would be present. So to me, they were not so surprising, but what I did find was quite intriguing is we couldn't see any detections of triclosan at reportable concentrations. So this is a very hydrophobic chemical. We know it's present in biosolids. We know it's also present in soils that have received biosolids in the US and Australia. So I was expecting that chemical to be picked up in our monitoring, but that wasn't. But what we do know is that the composition of the biosolids in particular is very variable. So it's affected by season. So you can get changes in the composition of the chemicals that are in it based on what's being used at different times of the year. It's affected by the course of the day as well. Like the effluent that's leaving a treatment plant can also change. So that does ensure that you've got this kind of complex medium that is being applied to the soils. So there's the potential for multiple chemicals to enter. So perhaps I've been looking at this data too much and nothing was too surprising. But yes, definitely some interesting chemicals that are present.
I think we're limited with time. I think there's some toxicity, the risk of these chemicals to soil and to the environment. That probably a lot of detail you need to explain. Maybe you could look at this chat and talk to or discuss with the questioners. I see people also post not maybe more comments about the Netherlands and Switzerland has banned the use of sewage sludge agriculture due to concern of toxicity. I'm wondering whether we have is there any regulation on the use of this in terms of agriculture consequence?
Yes, so there's restrictions on the use of biosolids and manure to land, but this is largely driven by the nitrate vulnerable zone directives and limiting the amount of nitrogen that's going onto land. But the presence of these emerging contaminants is not factored into the decision as to how much or what type of amendment can be applied. So that's where we thought this study was really important, was to first highlight that there are these chemicals present and to then think about what the implications are, because you can't keep changing or implementing regulation or policy without, I guess, that knowledge base of what's actually there in the first place.
Thank you. And just last minute, the last question, I want to look at the chat. So this one, Drew asked, briefly elaborate the method you use to identify the compounds in the soil without standards. And what's the confidence level of this identification?
So the targeted method, so all the methods were validated in-house, and they were quantified using deuterated internal standards. So I'm happy to provide more details if they want to follow up directly. The high-res mass spec work, so the chemical fingerprinting and then the non-target analysis, they were chemicals that have been identified to level 2 criteria. So this is one of it's the highest level of confirmation without comparing to an analytical standard.
Sorry, I missed the one actually very interesting one. A guy asked, is there any way to avoid this chemical for reaching the soil crops? I think that's really something everybody wants to know that.
Yes, that's a good question to end on maybe. So yes, there's different ways that you can process the materials. And for example, composting the manures has been shown to reduce the levels of antibiotics and veterinary medicines, and different types of processing under different treatments can degrade or can result in the removal of these chemicals. Biosolids, this also, you can also sort of treat this sludge further, and it can go under advanced processing, and this can also reduce the levels that are in the materials, but it's not going to completely remove everything. There's such a wide range of different chemicals out there. I think it's 350,000 chemicals are registered for use at the moment. So you're not going to be able to tailor all of your technologies to remove all of these chemicals to prevent them from being in the resources before you apply them to land. So we need to prioritize our efforts into the chemicals that are identified as being the most risky. And we also then need to combine that with, I think, better usage and disposal of these chemicals in the first place. So it's not putting the reliance on the wastewater industry to remove them, but if we can reduce usage and if we can create better sort of greener alternatives to these chemicals in the first place, then they're not going to be present in the resources that we then have to put this energy and time and cost into removing them. So yes.
Thank you. That's great. Thank you, Laura, for the excellent talk. Thank you, everybody, for listening and questioning, for your contribution. Okay, this seminar is ended.
Thank you.
Bye-bye.